Okay, so let's get started. So last week we talked about the number systems that we use in computer science. So this week we'll be doing some more practice with it, and we'll also be looking at some real problems from the past. So just a review, what are number systems? Number systems are different ways we can express numbers. We as humans use the decimal number system, which has 10 digits. And computers use the binary number system primarily, which only has 2 digits, 0 and 1. Last week, we also talked about how to convert between different number systems. So this week, we'll be doing more practice with that as well. Okay, so last week, I assigned homework, but it's not really like homework. You didn't have to do it. In the email, you should have gotten a document that had 5 extra practice questions. So today we will start by going over these questions. Okay, so question 1 asks, convert 147 in base 8 to base 10. So what did you guys get for the answer for this one? Yes, Lingxi, I see you're raising your hand.
I got 103.
Do you want to explain how you got that answer?
Okay. So the 7 is just literally 7, and the 4 over there is 4 times 8, which is 32, and the 1 at last is 64, and if you add all of these up, you'll get 103.
Very good. So let me just repeat what she said. So 147 in base 8 can be rewritten as 7 plus 4 times 8 plus 1 times 64, and that gives you 103. So very good. How about question 2? Which of the following has the fewest number of ones in its binary representation? Did anyone do this question? Okay, so for this question, how I would approach it is I would first rewrite each of the 4 numbers that are given into binaries. So I'll start with 9A7. So how we convert numbers from base 16 to binary would be, we would group it, every digit would correspond to 4 binary digits. So in this case, 9 is 1001, A is 1010, and 7 is 0111. So in total, for this one, there are 7 digits that are 1. Okay, so I'll just write 7 here on the side. For the second number, B14, base 16. So once again, every digit corresponds to 4 binary digits. This is 1011, 0001, and 0100. There are only 5 digits that are 1. If you don't know where I'm getting these numbers from, you can always draw out a conversion table to use as a reference. And for the next one, 7431, I think there's a typo here. It should say base 8. So for base 8 to binary, every 3 digits corresponds to so every digit corresponds to 3 binary digits. So there are 7 in this one. If you weren't here last week, that's okay. The recording for last week's video is on our YouTube channel, and it was included in last week's email, so you can go ahead and check that. It's okay if you can't follow along for this first part. We're just reviewing the 5 questions that I gave everyone last week. We will do some more questions in real time, and hopefully that will help you get caught up and get some practice. So for the last one, also in base 8, every digit corresponds to 3 binary digits. So 4 is 100, 2 is 010, and 6 is 110, 5 is 101. So there are 6 ones in this binary representation. So our answer should be B, because that one only has 5 digits that are 1. Okay, for question 3, what is the base 16 equivalent of 41375 base 8? So if we're converting from base 8 to base 16, probably the easiest way to do it is to convert from base 8 to base 2 or binary, and then go from binary to hexadecimal. So using the same technique as in the previous problem, 41375, in base 8, every digit corresponds to 3 binary digits. 4 in binary is 100, 1 is 001, 3 is 011, 7 is 111, and 5 is 101. So this is, now we're going to regroup it into groups of 4. So when we're doing the regrouping, we should always start on the right side so that if we can't group it evenly, we can always add leading zeros. So 1101 would be the last group of 4. Then 1111, 0010, and 100. So we can always add a leading 0 in front of that. So lastly, every group of 4 corresponds to 1 hexadecimal digit. So this is the same as 42F. Ooh, I can't. 42FD base 16. I don't know why it's trying for some reason. Okay, so that's it for the first 3 questions. So on the next slide, convert 2122 to hexadecimal. So for this question, we can use the reverse strategy or the shortcut. So if we're going to divide by 16, okay, so 10 corresponds to A. And then using this number, we will continue to do the division. Okay, so this is 4, and then lastly, this is just 8. So going reverse, our answer is 8 for A. And okay, I'll just skip the last question for now. I think this is kind of boring for you guys, so we'll just move on. If anyone has any questions, feel free to say it in the chat. Okay, so let's do some in-class practice now. Okay, so I'll give you guys some time to work on the first question, which is, what is the value of 657,383 base 16 minus 654,321 base 16 in base 8? So first, subtract these 2 hexadecimal numbers and then regroup it into base 8. So I didn't touch on subtraction or addition last week, but this problem is relatively straightforward because we don't have to borrow any digits. So you would approach the subtraction in the same way. I see someone solved it correctly in the chat. Okay, so I'll go over this question now. Does anyone want to explain? Okay, so for this subtraction, since we have no carryover, it's pretty straightforward. We can just subtract it how you would using base 10. There's no difference. So now we have 3062 in base 16, and we want to convert this to base 8. So how will we go about that?
Wait,
Does someone have a question? Okay, so first we would convert this to binary. So every digit corresponds to 4 binary digits. So I don't have space here. Let me do this on a new line. Okay. So 3062 in base 16. 3 is 110. 0 is just 4 zeros. And then 6 is 0110. And 2 is 0010. So now let's regroup it into groups of 3. So I'm not doing anything different here. I'm just regrouping the numbers. I don't have space. Let's redo this. And then every 3 binary digits corresponds to 1 octal digit. So if you got 30142 base 8, you are correct. Okay, now let's move on to the next question. How many 6s are there in the octal representation of the decimal numbers from 675 to 700 inclusive? So for this question, I would first convert 675 and 700, which are the endpoints. I would convert each of them to base 8. So how would we convert 675 to base 8? Okay, so we will use the shortcut method. So how would we divide 675 by 8? So the numbers are a little bit larger here. Okay, so for 67 divided by 8 is 8. And then we have so that's 64. We have a remainder of 3. Now we bring down the 5. So 35 divided by 8 is 4 with a remainder of 3. So let's keep going. 84 divided by 8 is 10 with a remainder of 4. And then 10 divided by 8 is 1 with a remainder of 2. So going in reverse, 675 in base 10 is the same thing as 1243 in base 8. Okay, so now we know what 675 is. Let's do the same thing with 700. Okay, 700. Okay, so let's first do the reverse division. So once again, this is 8, and then 60 divided by 8. So this has a remainder of 4. So this is with a remainder of 7. Okay, so we have from 1243 all the way to 1274 in base 8. And now we have to count how many 6s are in the numbers between and including 1243 and 1274. So the first number that would have a 6 in it would be 1246. The next one would be 1256. And then we would have 1260, 1261, all the way to 1266. 1267 is the highest one. So in total, there should be 11. So that's the answer for this question. And the reason is because 1266 has two sixes in it, so it will be counted twice. Okay, so now let's do the last question on this page. Evaluate and express in base 16 if both numbers are hexadecimal. Wait, I think something's wrong with this question. We'll skip it for now. Okay, we'll just do these questions then. Okay, first question, convert 6421 base 7 to base 10. Does someone want to explain this question? If no one wants to volunteer, then I'll call on someone.
Excuse me, I have to go to the bathroom.
Sure, you don't have to tell me. Does anyone want to explain? If not, I'll call on someone.
You just multiply it by the powers of 7.
Yes. Okay, so 6, 4, 2, 1, base 7 can be rewritten as 6 times 7 to the power of 3 plus 4 times 7 to the power of 2 plus 2 times 7 plus 1. So I'm just expanding it out into its full notation. This digit represents 7 to the power of 0. This digit represents 7 to the power of 1. This digit represents 7 to the power of 2. And this digit represents 7 to the power of 3. So that is how I got this expression. And if you evaluate it, you should get 2269. So that is the correct answer. Okay, so if you don't understand this, let's go back to the basics. So when we have 123, just a regular number, we can rewrite this as 1 times 10, 1 times 100 plus 2 times 10 plus 3 times 1, right? We all know this. So actually, this is 1 times 10 to the power of 2 plus 2 times 10 to the power of 1 plus 3 times 10 to the power of 0. So I'm doing the same thing with this number right here, except the base is 7. So instead of powers of 10, we're expressing it in powers of 7. So that is how I got 2269. Okay, now let's work on the next question, which is going reverse. We're going from base 10 to base 13. Convert 9876 to base 13. How do you get the 3? Which 3 are you talking about? This one? That just comes from the digit itself, the exponent. Oh, so this is, the 3 over here is the ones digit. So you can also express that as 10 to the power of 0. This over here is the tens digit, or 10 to the power of 1. And this is the hundreds digit, so it's 10 to the power of 2. So same thing, in base 7, this is the ones digit. This is the sevens digit. This is the 49s digit, or just 7 to the power of 2. And this one is 7 to the power of 3. So that is where I got these exponents from. Okay, so now let's work on the next question, which is convert 9876 to base 13. So I never formally introduced base 13 before, but you don't really have to know what that really means. You just have to know there are 13 digits, which goes from 0 to 9 and then A, B, C. So those are the digits you would use. Okay, for those of you who understand, please keep working on the second question. I'll just re-explain the first question since a lot of you guys weren't here last week. So when we have base 7, we are just using a number system that only has 7 digits, and those digits are 0, 1, 2, 3, 4, 5, 6. So we're used to having 10 digits, which goes from 0 to 9. But in base 7, we only have 7 digits. So when we look at a base 7 number, like in this case, 6, 4, 2, 1, we have to write it out using powers of 7 rather than powers of 10. So in math, when we represent our numbers, each digit each place value has its own digit, has its own value basically. So in base 10, we have the ones digit, we have the tens digit, we have the hundreds digit. In base 7, we're writing all the digits in terms of powers of 7. So the digit to the most right is going to be this, it represents 7 to the power of 0. This one represents 7 to the power of 1, or AKA the 7's digit. And this one is like the 49's digit, however you want to call it. But we're just writing it out in powers of 7. So it goes in order, 7 to the power of 0, 7 to the power of 1, 7 to the power of 2, and this is 7 to the power of 3. So that is why we can rewrite this number as 6 times 7 to the power of 3 and plus the rest. So for the next question, I know some of you guys have been waiting. For the next question, we're going to do the reverse. So basically we will divide it into 13. So last week I taught dividing like this, but sometimes when we have big numbers like this, it could get ugly. So just to make it more convenient, I'll just do the standard division. So we're going to divide it into 13. So this is 7. 7 times 13 is 91. So this is 77. And then this is 5, 65, 12. 126 goes into 13 9 times. So this is like this. So now we take this number and then we divide it again by 13. So this is 65, 109, 8 times 13 would be 104. So 5. So the remainders are really important. That's what we're looking at. And then 58, let's keep dividing that by 13. So 4 times 13 is 52. And that is 6. And then this 4 is going to go here. So now we go in reverse order. So the answer should be 4, 6, 5, 9, base 13. So that's our answer.
I publicly apologize. Sometimes my math just doesn't math, and I just completely freeze. Sorry that I just... Some reason 9 minus 4 is 5. Sorry, I thought 9 minus 4 was 5 for whatever reason. I don't know.
Okay, so for the last question, we're dealing with decimals here. So we haven't ever really worked with decimals before, so I'll just give another example, I guess, to start off. So let's say we have 123.5 4, 5, 6. So 1 can be written, so this is 1 times 10 to the power of 2 plus 2 times 10 to the power of 1 plus 3 times 10 to the power of 0. Now, when we get to the decimals, we can go in the same way. So we're just going to keep subtracting 1 to the exponent. So this is going to be 5 times 10 to the power of negative 2 plus 6 times 10 to the power of negative 3. So we can do the same thing for base 2. So for example, this digit would be 2 to the power of negative 1. This would be 2 to the power of negative 2. This is 2 to the power of negative 3, and this last digit here represents 2 to the power of negative 4. So the rest is just the same, isn't it? So we will just multiply the number by the actual number that's represented by the digit and add them all up. I see many of you already have the answer in the chat. So this is the same thing as 1 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 1 times 2 to the power of 0. And getting into the decimal part, 1 times 2 to the power of negative 1 plus 1 times 2 to the power of negative 2 plus 0 times 2 to the power of negative 3 plus 1 times 2 to the power of negative 4. So the zeros, you can ignore it because they don't actually have any value. So this is 8 plus 4 plus 1. And 1 times 2 to the power of negative 1 is 1/2 or 0.5. This is the same thing as 1/4 or 0.25. And this is the same thing as 1 over 16, which is 0.0625. And adding all this up, you should get 13.8125. So that is the decimal representation of this number. Okay, so that is all for the questions, I think, for this week. And before we move on, I wanted to just talk about something else really quick that's useful in computer science, but it also relates to binary, which is how computers store data. So as you know, in computer science, we store data using bits. So a bit is a single value or container that can only store a 0 or a 1. And in Java, let's say an integer has 32 bits. So now I want to ask all of you, how many numbers can it actually represent, or what is the range? In other words, what is the highest number or integer that can be expressed in an integer in Java, for example, where there are only 32 bits? So 1 bit can either be 0 or 1. And when you have 32 bits, that means you can have 32 zeros or ones. Okay, so let's first make this more simple. Let's just do 8 bits instead of 32 bits. So the highest number you can express technically would be just 8 ones. So if we had 8 ones, in binary, that is equivalent to 255. So that would be the highest number we can represent. However, in computer science, we have to account for positive numbers and negative numbers. So in actuality, even though we have 8 bits, only 7 of them are actually useful to us because the first bit is always responsible for the sign. What I mean is either positive or negative, because in real life, we have not only positive numbers, we also have negative numbers. So the first bit represents the sign. 0 is for positive and 1 is for negative. So the remaining 7 digits or bits are actually useful for us. They actually represent the value of the number. So if we have 7 ones, that is the same thing as 127. So how did I get this number? So we only have 7. We only have 7 bits that are actually available for use. So that's why it's 2 to the power of 7 minus 1, which is 127. So that is why if we have 32 bits, then the highest number we can express is 2 to the power of 31 minus 1. Since we have to divide by 2, since the first digit is accounted for the sign. Okay, this is not something you have to know for the contest. It was just something aside that is in computer science as well. Okay, so this last question. Okay, so the purpose of the first one is for the sign. So because we have positive numbers and we have negative numbers. So that is why the first digit is used to tell a computer if this is a positive number or a negative number. So a 0 is a positive number, and a 1 is a negative number. So this last one right here was actually the coding problem on last year's contest. So it reads, given 3 positive integers n, b, and s, Generate the next n numbers in base B, starting with S in the given base. We guarantee that the base will be between 2 and 9 inclusive. We will guarantee that S is a valid number in base B. Find the base 10 value for the number of times the largest possible digit in the given base is found among all of the digits in the numbers generated. For example, if n is 15, b is 8, and s is 2, then the numbers generated are 2, 3, 4, 5, 6, 7, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, and 2, 0. The largest possible digit in base 8 is 7, which occurs 2 times. So basically, one of the parameters here, which is b, is the base. And s is the starting value. That is why the numbers generated starts with 2. And n is the number of consecutive numbers that you have to generate in that base, starting with the starting number. So if you notice, the program should accurately generate the next 15 numbers after 2 in base 8. So that is what this question means. And so the input is 3 integers, n, b, and s, and it will guarantee you that it's an actual valid number and the base is between 2 and 9. And the starting value in the given base will be no more than 16 digits. Okay, and we have some sample inputs and outputs, so you don't have to worry about that for the bottom. So I don't actually want to solve this question in class. I just wanted to present how you would solve it. So for dealing with different number systems, it's probably best just to write 2 functions in whatever programming language you're most comfortable with. One function should convert from base B to base 10, and the other function should convert vice versa. It should convert from base 10 to base B. So what you always, for this question, you probably want to convert the starting number from base B to base 10. And then after that, you could create like an array or some sort of data container or list that will help you store the next n numbers. And since you converted the first number from base B to base 10, you can do the rest of the calculations in base 10. So you could use a for loop for that, which would probably be the easiest. And then after you have generated the array or the list, you can go through the array or the list and use the function you created to convert each base 10 number back to base B. So after doing that, all those steps, you should get this long chain of numbers, but that's not what the question is asking. The question is asking, how many times does the largest possible digit appear? So this step is probably easier. So you know that in base 8, the largest digit is 7. So you can go through and check how many times the digit 7 appears. So if you know the largest possible digit is 7, then we will count how many times the digit 7 appears in all those numbers you generated. So in this case, 7 only appears 2 times. So your output should be 2. I think I didn't explain this clear enough, but um so you have numbers over here, and in numbers, if you want to see if a certain digit appears, it's probably easiest to convert the numbers to a string. And then using string, for example, the numbers that have 2 digits, you can use a string so that you can use each index and find if the largest digit appears. Okay, so I think that's all there is to today's lesson. Feel free to think about the last question a bit more if you have time, or even better, I encourage all of you to write out 2 functions that will convert from a certain base b to base 10 and from base 10 to a certain base b. When you're creating the functions, try to use the mathematical reasoning about how you would do those conversions that we went over a little bit in today's class. We did lots of practice problems, and so use the math to do the to write the code for the functions. And the slides will be in the email and also in the shared Google Drive. They should be under slides. So that is where you can find all the slides and the notes from class. And yeah, that's it. I hope you all have a great week. Our next class will be next Saturday as usual. And if you have any questions, feel free to email me.
Bye.
Thank
Bye.
you. Bye.
Thank you.
Bye.
Bye.
I'm actually gonna code that for you to Eclipse right now. Thanks, bye.
I got nothing today. What is it all talking about?